Okay, welcome everyone to today's seminar. We're very happy to have Jorrit Kruthoff from Stanford, who will be telling us about bootstrapping matrix quantum mechanics. So Jorrit, please take it away.
Thank you so much, Hugo. It's great to give a talk here, and thanks for the invitation. Yes, so today I want to tell you a little bit about some work that came out last April that I did with Sean Hartnell and Chijie Han. And it's about bootstrapping quantum mechanics or matrix quantum mechanics. And it's basically what I want to explain is sort of a technique or an idea that we developed in this work. And then I want to exemplify it with some examples. And contrast it a bit with some other methods and see what the logic is here. And again, to reiterate, like please interrupt whenever you have questions or things are unclear. And I'll have some open questions at the end, so hopefully we can have a discussion about those as well. All right, let's get cracking. Right. So in general, right, solving a theory, say a CFT, a QFT that describes some physical system, say some critical point of some material, whatever, is usually hard, and because we need to employ perturbation theory, or we need to employ some other method that approximates the actual system, and to have any analytic tractability, such approximations are necessary. And of course, in the course of the few decades that we're now facing these things, many different perturbation theories have been developed, and many are very elegant, very powerful. But on the other hand, with the rise of numerics, we can also try to attack solving these theories on a computer. And okay, there's many different ways of trying to solve, trying to integrate certain processes. Of course, we can have numerical integration, we can have Monte Carlo, and there's many, but today what I want to highlight is sort of a numerical bootstrap approach. And of course, with this we know very well from the conformal bootstrap or modular bootstrap for conformal field theories. But here I want to take a slightly different approach and apply to a slightly different set of systems, namely those that don't have any spatial locality. So there's only going to be a time direction, or not even a time direction at all, that we will be dealing with. So that's sort of the setup that I want to. Of course, this bootstrap, as people know, can also be applied analytically, but here I want to focus on the numerical side of it. And we'll see that it's still complicated, but so that we can get some cute results. So what is this bootstrap philosophy? Again, is in the catchphrase, I would say it's constraining data with consistency conditions. And so there's some data that defines your theory. For instance, in a CFT, you would have scaling dimensions or critical exponents, and you'll have the OPE coefficients, the coefficients of 3-point functions. And then the rest is fixed by conformal symmetry, provided that you satisfy the crossing equation. And so crossing symmetry, and perhaps you want to throw in unitarity in there as well, are the consistency conditions. And with those conditions, those equations, you try to find the possible values that these deltas and CIJKs can take. And this has been very successful. For instance, people have found certain CFTs by employing this program, and could really find like isolated points in parameter space that give you a particular consistent conformal field theory. For instance, the Ising model, or the 3D Ising model, 2D Ising model, those type of theories came out of this program. So today, what we'll be seeing is that the data that we're going to look at is the energy of the system, so the expectation value of the Hamiltonian, and the say ground state. Roughly speaking, we'll be looking mostly at ground state expectation values, and we'll see that not every value for the energy and the expectation value of these certain operators is going to be consistent with positivity of a correlator that looks like this. And so here O is some arbitrary operator made out of sort of a set of basic operators. I'll be much more precise in a moment. But you can think of it as the, say in quantum mechanics, O could be a linear combination of the X operator in quantum mechanics, or X squared, or X to the 4. And so when I consider this type of object, which of course needs to be positive, then I get a whole chain or a whole sum of different operators built out of these X's in the quantum mechanics case. And so those expectation values are going to be constrained by this positivity condition. And that allows me to sort of carve out the parameter space, the energy versus the vacuum expectation values, and to pinpoint certain points in that parameter space that give a consistent theory, or a consistent set of variables. Okay, that's a little bit abstract, but I just want to get this get everybody on the same page here. And of course, this type of bootstrapping that I want to employ here is not new, but yeah, our implementation will be slightly different. And just to reiterate sort of the logic, which can be found in papers by Anderson and Krushansky from 2017, and Henry Lin from early this year. And actually mostly we were inspired by this paper by Henry Lin, where he applied some of the logic that I will be presenting to matrix models. And here we're mostly be interested in quantum mechanics or matrix quantum mechanics. But roughly the idea is that if I consider some operator O, which is a linear combination of these objects that I denoted M sub I. So M sub I could be, in the quantum mechanics case, would be X to the I, to the operator X to the ith power, or it could be a matrix to the ith power. It could also be a Wilson line with a loop specified by I. Then this, if I then form this object, this O dagger O correlation function, and I compute it in the vacuum, or in basically any state, then this needs to be positive for any such O that I can construct. That means that the matrix that I form from just these M's, so the matrix that I've denoted here, must be positive semi-definite. And only then I can guarantee that for whatever CI I pick, this object is going to be positive. And so the constraint that we're going to focus on is this positive semi-definiteness, and we'll see in various examples how that plays out. Positive semi-definiteness means that that all the eigenvalues of this matrix need to be positive. So that's an easy thing to implement numerically. We'll see that there's certain obstacles in how to prepare this statement on the computer, but we'll get to that. Now, of course, if I have all these different matrix elements, these Mij, then there will be kind of a hopeless situation, right? Because then I have to constrain all possible expectation values separately, and so the parameter space, the data, will be very large. And so it's sort of different, sort of similar in spirit as the conformal bootstrap, where you just have the CFT, the deltas and the OPE coefficients, and not just any correlation function that you need to fix. There's some reduced set that you can work with. And in this case, we'll be looking at models that also allow such a reduced set of variables to fix all the higher correlation, all the higher point functions. And this recursion relation, for instance, in the matrix models, is usually referred to as the loop equations. And so the loop equations relate correlation functions of smaller operators to bigger operators, or to double trace type operators. So these loop equations only exist in certain special circumstances. They certainly don't do in any model. And in fact, so the case that we'll be looking at, there's time, and these loop equations are rather complicated. And so how do you think about these loop equations? Are basically the Schwinger-Dyson equations. You write a total derivative in the field space, or in this case for a matrix integral, and then you have a relation. Because it's a total derivative, you can work out the right hand side, and then that has to be 0. So there's some simple way of getting these loop equations, but if time is involved, we have a kinetic term, and in that case, the loop equations will involve integrals over time as well, or just derivatives. But and so these equations become rather complicated to solve. In the matrix model case, so when there's no kinetic term, no time, which was the case studied by Henry Lin, and also in this paper by Anderson and Krushenski, in that case, you don't have these integrals or don't have these time derivatives, and you get the genuine loop equations that are much more simpler to handle, and you can easily put them on a computer, for instance. Right, so we need sort of a slightly different thing, because this loop equations for the matrix quantum mechanics is going to be too complicated. So what we will be looking at is a sort of slightly different type of recursion relation. And it's a recursion relation that has the following form. So H here is the Hamiltonian, O is here whatever operator, and the expectation value here is taken in a state that commutes with the Hamiltonian. So that if I compute the expectation value of the commutator of H with O, I get 0. And if for any operator that I put here, I get a new constraint. And so I can put in some operator, compute the commutator with h. That gives me a certain expression. Compute the expectation value, and then I know that that has to be 0, but that is going to relate correlators of different operators with each other. And so instead of the loop equations, I'll be using these type of constraints. And these type of constraints are, of course, more in spirit for ground state expectation values or vacuum expectation values, or just in some energy eigenstate. So those are the things that I want to relate these operators with. So yeah, enough of this sort of abstract stuff. Let's see how this works in an example, because I think that might be illuminating. Are there any questions at this point already? Okay. So let's consider this anharmonic oscillator. So if the Hamiltonian H is p square plus x square, this is just a harmonic oscillator. And I'm sorry, okay.
We can still hear you.
Yeah, something went wrong with my headphones. And we have here an interaction which makes this an anharmonic oscillator with a coupling constant G. So this is just simple quantum mechanics, nothing very fancy. And now, for instance, these operators O can be any power of x and p. So x to the s and p to the t, where s and t are positive integers. And so to give an example, if I take O to be x times p and I feed it into this condition, what I get is that the expectation value of p square is related to the expectation value of x, and x to x squared plus x to the 4. And then I can use the fact that, okay, the expectation value of h is going to give me the energy, plug this p square in, and I can eliminate p from the energy. And so this statement here is just a viral theorem. It's the relation between the kinetic energy and the derivative of the potential. All right. Now, similarly, you can play around with different types of operators. See, that's the nice thing about this approach, is that whatever operator you put in, you get a new constraint. There might be relations, but the constraints might be redundant or in some sense. What you can do in particular is to use different O's, different operators O, to get different relations between operators, and in particular derive certain recursion relations between operators, different powers of x. You can explicitly eliminate any powers of p in this game, and the recursion relation that you end up with is something that I put here in this blue box. So remember, t is here an integer, and so here you see a recursion relation that relates the different correlation functions. Now, furthermore, we know that since this potential is symmetric, that any odd power of x is going to be 0. Correlation function of any odd power is going to be 0, and x to the 0 is normalized to 1. And so with that, here you can see that these steps are always steps by some even number. So when I set this odd to 0, I can completely fit, and I have this condition, I can completely find all solutions given two initial conditions namely the energy, that's right here, and the expectation value of x squared. If I specify these two, then can get any other higher point function. Right, so this is sort of the analog of the recursion relations that the loop equations that you would have in matrix models or matrix quantum mechanics, things like that.
Sorry, I have a question.
Yeah.
Sorry, I missed this point. You are deriving these identities using this expectation value of the commutator of H with O is 0. Like, why should that be true for any arbitrary operator? I missed that point, sorry.
Oh, it's true for any operator, but it's not true for any state. So here I chose a state that commutes with the Hamiltonian. And so I act with this H on the right or on the left. I pop out the energy eigenvalue. And then for the other term, I also pop out the energy. So, but there's a minus sign, so these things always cancel.
I see.
Yeah, so it's this particular state that I'm using. Yeah.
Thank you.
Yeah. Okay, so that gives us a specification of these other endpoint functions. Yeah, this I already said that we could eliminate P. And so now to set up this bootstrap, and so to implement this positivity constraint, this O dagger O expectation value needs to be positive. I can consider operators that are linear combinations of x to some power. So these will be my operators, and these MIJs that I was talking about, which only involve these x's, will then be x to the I plus j. And so this matrix involves now all these different powers of x, and this matrix needs to be positive semi-definite, meaning that the eigenvalues need to be non-negative. And right, so this is an easy thing to implement, and yeah, let me just show you the results for that. All right. So what do you see here? So here you see that this k here is the number of terms that I kept in this operator O. So here, remember that there's an upper bound. Okay, so this will give me some finite dimensional matrix Mij. Of course, if I increase k, I'm going to take more expectation values into account. There's more eigenvalues that need to be non-negative, and so there's going to be more constraints. And right, so that's this k. And then here on the x and y axis, you can see the energy versus the expectation value of x squared. So these are the two numbers that I cannot fix with this with the recursion relation, their input. And then I just scan over all different inputs, all different e's and x squares, and then see in what cases I have a positive or I have non-negative eigenvalues in this matrix. And you see that there's an island formation around the true spectrum. So here, this red cross is a true spectrum, the true eigenvalue for the ground state in this top figure. And you see that, okay, first I have some constraint which involves 7 different operators in this O. And then if I increase that, you can see that it already rapidly converges to an island that is sort of very narrow and close around the true energy eigenstate. And the nice thing in this case is that we have a discrete spectrum, and so different energies. There's going to be different energies that are going to be consistent, and so we can also capture here the first excited state, for instance. And that first excited state, we need a bit more constraints. It's a bit higher energy. It's a bit more complicated to get it, apparently. And we can see that this island formation and the convergence is very quick. So this is a sort of a fun thing to do on a computer. That's very easy to implement. And you can really quickly see that these islands become very small when you increase these constraints. So so this is basically the story for the quantum mechanics, and just served it a little bit as a exemplification of the method. Is this clear? Do people have questions about this, or should I just move on to the matrix quantum mechanics? All right.
I have a question, Jorrit.
Yeah.
How do you like? What is the input? The different input to get the first plot or the second plot? Where do you input the fact that the second plot is for the first excited state?
Oh, you don't actually. So you just find this. So what you do is you scan over all different parameters of this energy and x square, this expectation value.
Okay.
And then you see that there's different islands that are consistent with positivity of these eigenvalues.
Okay. Okay. Thanks.
Yeah. Thanks for the question. Okay, so let's move on to the matrix quantum mechanics case then. Now, in this case, we'll have matrices instead of P and X. So these big P's, from now on, I'm basically only going to talk about matrices. These P's and X's are going to be n by n matrices. I'll first start with a simple one matrix model, but there's one P and one X. And then later we'll also look at the two matrix model, where there's two momenta and two flavors of matrices. Now in the one matrix case, we can again benchmark our method, because there's you can solve this exactly by going to the free fermion description and using large N. And so this matrix quantum mechanics, as many of you know, is very relevant for non-perturbative definition of quantum gravity. For instance, the BFSS model or the BMN model, both of which have fermionic matrices as well. So that's another complication, but still it's doable. I won't discuss it today though. And the CS1 matrix model, and there's many more different matrix models that you can look at, or matrix quantum mechanics that are relevant. So the idea here would be to compute certain simple observables. So in the quantum mechanics case, we looked at the expectation value of x squared, and we could iteratively get the higher point functions. Here, that won't be so easy to get all these higher point functions. In fact, we'll not be able to write down a closed recursion relation for all of them. But the operators, the expectation values that we're after, and things that we can compute also in the exact description using free fermions. Of course, we can compute anything there, but things that we'll be looking at is, for example, the expectation value of the Hamiltonian, trace x squared, the trace of this commutator square, to diagnose what happens as we change couplings, what happens to the commutativity of, say, in a two matrix model. Right. So the thing will be, we'll still use the same ideas to implement this bootstrap approach. So we still have this h, o commutator being 0. And here again, there's the state is going to be an eigenstate, or the state that commutes with the Hamiltonian. We'll see that this state can also, if there's additional symmetries, we'll also want to have this state to be symmetric under those symmetries. But the important thing here is the difference with the quantum mechanics, that here we have relations between operators and no recursion. That I mean that, okay, you can't get arbitrarily high point functions using this method. Mostly because since this O that we're gonna look at is a single trace operator, the commutator can give double trace operators, and so and then we need to use large N to factorize these double trace operators into products of single trace operators. So here we see that the large N is also very important. And in fact, this bootstrap will be in the strict N to infinity limit. Okay. Now, as I said, this state that we'll be looking at could have the theory that we're looking at can have more symmetry, and then the state also needs to be symmetric under that, or that's a sort of simplification that we're going to look at. For instance, in the matrix quantum mechanics case, there's an SUN symmetry that basically conjugates the matrix, and by some unitary or some SUN matrix, and the generator of that symmetry is this operator G. It's this commutator of x and p plus the identity, and we want states. So basically, we'll be looking at a gauged matrix quantum mechanics. So we'll be looking at this at states where that are invariant under this symmetry. Now that gives another constraint, and that gives the following constraint. Because if G here acts on this bra, it will vanish. And so if I compute this trace of G times O, I get again some relation between operators, and that needs to be vanish. That needs to vanish in that symmetric state as well. Furthermore, it's important to impose a reality condition that O dagger, the expectation value of O dagger, is the conjugate of O, of the expectation value of O. And furthermore, it's important to use the cyclicity of the trace. And so here in the quantum mechanics case, we can, even though the operators as quantum operators might not commute, X and P do not commute, you can still permute them using the cyclicity of the trace. And by using the cyclicity of the trace and the way these operators commute, you can again find new relations between different orderings of the operator, and that gives yet another set of constraints. So let me look at an example here. So this is a simple example where you have just the harmonic oscillator version. This is just an unharmonic oscillator version of the quantum mechanics problem that I discussed. And this model can be mapped to the free fermion description. It becomes a non-relativistic free fermion, and we can solve things there, and we can compare our results with that model. Now, just to go through the similar analysis as we did with the quantum mechanics case, if we have this operator O and to be this trace X times P, then you can again derive a relation between trace p square, trace x square, and trace x to the 4. And you can again find the energy in this way and things like that. But before, in the quantum mechanics case, we could eliminate p. But here, because there's different types of orderings possible, it's not so easy to eliminate p. And p appears in this trace, and so we only get expectation value of traces and not expectation value of individual matrix elements. So the symmetry constraint. So if O is the identity operator, so there was this constraint. G was the symmetry generator of the SUN. Then this trace of G also needs to vanish, and that gives a relation between the trace of XP and trace of PX. And so here you see that this has to be I times n squared, where you show using simple commutation relations for these matrices. If you do O is trace x square, then this trace x square only picks up terms by commuting with this trace p square, and then you can easily derive that gives a relation like this. And so you see that in this different types of O give you different types of constraints, or different types of relations. Sorry, and so then again we can try to build this matrix Mij. And so we take this operator O, and now we take some linear combination of the identity operator x squared, x, and p. And so that will be our O. And when we compute this matrix Mij, and we strip out these coefficients Cij, if you remember, then this matrix Mij is going to be looking something like this. And so this means that, okay, I contract this I and I, x, x squared and I, x and I, and so on. And here the odd powers or single p operates again 0. Here we're in the ground state, so this single powers of m are 0, and odd powers are also 0. So here we have all zeros, but then here the interesting stuff happens in these two blocks, and we get these different operators, these different expectation values here. And now you can see that, okay, we can use the constraints that we found here to simplify this expression. So this trace p square, we can use, for instance, this top constraint to simplify that, and to write it just in axis. And then here, this trace xp, we can relate to this trace px by using either of these two. Essentially, these two together fix entirely the expectation value of these off-diagonal pieces to be n squared over 2 times some I or minus I. Right, so this matrix needs to have now positive or non-negative eigenvalues. And so if you look at this top block, you can see that it already gives a constraint if I did compute the determinant, for instance, of this little piece. That means that this trace x to the 4 must be bigger than this trace x squared. And likewise, there are other types of constraints that you can consider. But yeah, that's sort of the logic here. And if, whenever we encounter double trace operators that in this simple example didn't really were not really necessary, we use large N factorization. Okay, so this was just for some simple set of operators O. In general, they will have they'll be having many possible operators. Say I want to construct all operators of order length L, or up to L, then there's 2 to the 2L operators that I can make approximately. And there's those relations between how you do that. So there's many O's that give many different relations between these operators, but also a much bigger matrix, and the sort of operators that we didn't fix also become larger. Right, so remember, or you can see here that since we can't get this recursion relation, and this trace x to the 4 is still sort of an unknown, and so we need to the sort of the optimization problem becomes higher dimensional. So before we had just x squared and e, here it becomes a bit more complicated. There's trace x to the 4. In this case, is also not is also an input. So although we get more operators, the sort of the search space, the data, becomes bigger as well, and that makes it still fine to implement numerically. But you see that there's at some point when you have more and more matrices, it's going to be more and more complicated to do this sort of bootstrap. Now a few comments. Since we work at large n or at infinite n, the spectrum is continuous, and so we won't get these islands. And so, as Bernardo was asking before, if we have a discrete spectrum, you can easily find these different energies that are allowed. But here, since there's a continuum, we need to do something slightly different from that. And what we will be doing is we will just minimize the energy. And so we'll be looking at the ground state and ground state correlation functions. And by using that, we'll find a lower bound on the energy, of course, because the true ground state must be in the allowed region. Okay, so let me just flash some results here. This is the energy, and here appropriately scaled with power with n squared. This is the ground state energy, as I said. And in the lower plot, I plotted the trace x expectation value of trace x squared. These are both functions of the coupling G. Now you can see that this L is relatively small, but you can see that when I increase L, the numerics quickly converges to the exact answer. So the exact answer is in this free fermion approach. And you can see that if I have operators just of length 2, which is basically the simple example I showed before, it's not that good, but when you increase L already by 1, you'll get a pretty good fit, and then even higher, it becomes even better. And so the convergence is pretty good. Yeah.
Can I have a question? So do you know what's happening as G is increased? I mean, if you keep say L equal to 4 and you go to very large G, like would it matter, or like you would expect that you basically are spot on the exact solution?
Oh, when G increases to much higher values.
Yeah.
Yeah, then.
Do you need more L, like bigger L, or you expect that like it doesn't matter?
No, that doesn't really matter. It's only if there could, I guess in this case it's simple enough. But for instance, say you have some phase transition at some large G, right? That this energy is going to do something funky. Then you might need more constraints, because then this curve is going to change very rapidly. You need much more constraints to get that on the nose. But in this case, I think there's no phase transition or anything like that. And so at large G, we expect this to be not altered by by including more constraints or less. The constraints are this matching is just going to continue for larger G.
Thanks.
Yeah, thanks for the question. That's a good point. Right, and so the trace, the expectation value of trace x square is also going to converge very quickly with this method. Okay, so this was just the single matrix case where things are still exactly solvable. Let's now move on to a slightly more complicated example, and this will be the most complicated example I will discuss today, is with two matrices. So here I want to look at the following Hamiltonian. There's the kinetic term again, and then there is a mass term for these matrices, and there is this commutator of x and y square with coupling G square. And by appropriately rescaling your matrices, you can easily convince yourself that physical variables just depend on this ratio, m squared over G to the 4 thirds. And since we have two matrices here, there's a symmetry that relates the two matrices. It's an O2 symmetry that's generated by this particular rotation in matrix space. And if we look at symmetric states, right, this constraint even gives more states, and so or even more relations between operators. And especially the ground state will be in the singlet of this symmetry, and so I'll be using this symmetry as well in this two matrix case. Okay. And of course the whole logic now repeats itself. I construct this O, I construct relations, and try to find the constraints where the eigenvalues are positive, and the results of that are shown here. So the energy here is given. It's again order n square, and here at the 12th coupling n times G square. And so here you see the constraints with Ls3 and Ls4. So here Ls, because we now have two matrices, there's many more combinations that we can make. Right? We can certain strings of operators are now inequivalent because I have inequivalent operators that before in the one matrix case were the same. And here you see that, so for Ls3, the constraints are not enough. But if I increase L to 4, then you see it becomes much better. And here in these black dashed lines is an Born-Oppenheimer approximation to the ground state energy. And it gives both a lower bound and an upper bound, because in the Born-Oppenheimer approximation, right, in that case we diagonalize one of the matrices, say the Y matrix. We diagonalize that, and we write an effective theory for the axis, and in that case, this is the Born-Oppenheimer approximation, and then by carefully analyzing what terms to keep in that approximation, we can both find a lower bound and an upper bound. And so, I mean, of course, if it's a variational, in the variational case, we get a lower bound in the Born-Oppenheimer. The true bound Born-Oppenheimer, as we know from condensed matter, gives an upper bound. So we get these two different dashed black curves, and you see that if Ls4, this lies neatly within this this band, And if you compare it to, say, Monte Carlo simulations of this particular model, at the point where the mass is 0, so this is m is 0 or g to infinity, then you find a perfect agreement. So here, if we extrapolate, just to come back to Michael's question, if you extrapolate this to high G, then this agrees perfectly with the Monte Carlo results. So that's at least for the energy, that's a very good check of the method. And also for the expectation values, I don't quite remember which one of these two that was, but there was this top plot. We can also extrapolate to the massless point, and then we also agree perfectly with the Monte Carlo result. So the fact that, okay, this converges within this band also gives us confidence of these these plots, that they also converge to a final curve when we include more and more constraints. If we include more constraints, this process is going to take quite some time. I don't remember quite what the runtime was for this case, but it's order of days, that maybe a week or something to get these results. One thing that I want to highlight here is that at large G, you can show or we can verify that this goes to a finite constant. And so this means that at large G, the matrices X and Y are still non-commuting. And this is different from what happens in a matrix model of two matrices, where at large coupling, for a similar model like this one, they would be commuting. So that's one observation here. Okay, so just to reiterate the logic. So what I told you today is a bootstrap method, just formulated at infinite n. And so there's sort of 5 sort of assumptions or 5 relations that I employ. So first of all, we have a symmetric state. That means that, okay, we have symmetric under all the symmetries that we have, plus the commutator of H with the commutator of the state with the Hamiltonian must be 0. This plus sign is not the mathematical plus sign, but just and, I guess it's a bit of a typo. And the second point, of course, this relations, the H, O commutator in that state is vanishing. There's the SUN symmetry constraint, plus possible other symmetry. We saw the O2 symmetries when we had 2 matrices. Then there is the reality constraint. And lastly, there is a cyclicity of the trace. And so these 5 conditions, I would say this is maybe an assumption, the first one, but then the rest is constraints that you get, or relations between different operators. So these are sort of analogs of the loop equations. And then the bootstrap is to write down a list of these pure single trace operators, OI. So they will be trace X squared, trace XP, these type of things. You make some vector out of it. That will be the O, and the OI would be sort of the trace X squared part of that. So to say the basis factors. And then you construct this object, this O dagger O, and then each of these matrix elements needs to be so this matrix needs to be positive semi-definite, and that gives that allows us to find regions where we have consistent vacuum expectation values. And yeah, this is a form of positive semi-definite programming that you can also see in the Bootstrap literature. Although here there's some quadratic constraints as well, which mostly come from the cyclicity of the trace. But also, yeah, if there's double trace operators, that could also give rise to quadratic constraints. Yeah, and
can I have a question still?
Yeah.
So regarding the first point, right? Like you said that the symmetry is an assumption, right? But like if your ground state spontaneously breaks on symmetry, like.
Oh, you mean right? If there's some spontaneous symmetry breaking or something. Yeah. Then that's an interesting question. In that case, what do
you do then?
Yeah, what you would see like this, if you don't know this beforehand and you would impose these constraints, it would be like you won't find any minimum, right? So the program wouldn't end, it wouldn't converge to something. That would be a signal of that, for instance. So that in that way you can discover this spontaneous symmetry breaking by saying that, oh, if this Bootstrap program doesn't converge and I still have some bounded potential, so that there should be some ground state, then perhaps the symmetry of the ground is spontaneously broken.
But you mean like you basically run your program and try to see what you get, like, and if you don't get anything for a few days, like you would give up, or like you say that there's like a better criterion to know it, say, from beforehand?
Oh yeah, I don't know of a better criterion beforehand in particular, but from this sort of Bootstrap method, I would expect that the method will just fail to converge. And so saying basically that there's no expectation value of these operators that is consistent with these assumptions. And so then anything will be disallowed. And then, okay, what you can do then is say, okay, you relax these symmetry conditions. So you do that, then maybe you can find a constraint in that case, or you can find an allowed region in that case. It's of course a bit hard to test whether things do not converge, but yeah. But that would be my my expectation in that case. Yeah.
Thanks.
Yeah. Thanks for the question. That's a good point. Okay. And yeah, so this is sort of the logic that I try to convey, and I tried to show that in various examples and show that it works pretty efficiently. So let me just get to the end then, the outlook. Now in the past, of course, this whole matrix quantum mechanics, of course, very interesting, especially regarding the implications for some non-perturbative definition of quantum gravity. There have been great efforts in trying to compute observables in this matrix quantum mechanics, and in particular for the BFSS model at finite temperature. And one of the leading figures there is Masanori Hanada, but there's many others that have also contributed to that field. And this is more a Monte Carlo approach. Of course, I'm not an expert on what they specifically do, but our Bootstrap method should be applicable to that case as well. Maybe not necessarily at finite temperature, but I guess we can work in a thermal state, and then our method also works. Of course, one of the obstacles there is that BFSS has 9 matrices or something, and 16 fermionic matrices, if I remember correctly. So it becomes a bit more. There's going to be many more matrices, You can also do the BMN model where there's less matrices. But of course, there's also supersymmetry. So there's many more of these symmetry constraints or symmetry relations that I talked about. And in particular, we know that that there's some supercharge. And so instead of our commutator with H, we can look at commutators or anti-commutators with the supercharge Q alpha. And of this alpha, I think there's again, say 16, but don't pin me down on those numbers. And we can use those constraints to find more relations between operators, and that might help us a lot. This is sort of an ongoing thought that we have. As I mentioned, yeah, other things would be BMN or mini BMN. There's just less matrices, still supersymmetry. Here, of course, Michael's question becomes very relevant. And what happens to supersymmetry breaking, for instance? So in the Marinari-Parisi model, which is just a simple matrix quantum mechanics, which is still a single matrix, but it's supersymmetric. So there's one fermionic matrix. Then you can also look at potentials that break supersymmetry spontaneously, and then we can maybe see in a bootstrap what happens, and then the expectation would be that the bootstrap program is not going to converge, as I mentioned earlier. Now, there's also other sectors in the theory that we can possibly probe with this method. We focus mostly on the singlet sector here, but what about, say, the adjoint sector or other sectors? And for instance, in many cases, these other sectors are important to analyze as well, especially if there's some sort of black hole type physics going on, because that is supposed to be some soup of whatever other representations that they're present in the theory, other sectors. And finally, we can wonder about time dependence and so correlation functions, but that might require us to know many more relations between the operators. We need many more constraints, and so this is a bit more complicated, especially if we do finite time difference. And in that same ballpark, I guess, is the Candice method. This bootstrap method seems to be perfectly well applicable to field theories as well. Of course, there's spatial locality, and so you have fields at every point in space, and so you need to relate those to each other as well. But that can possibly be done by some symmetries. Say there's some translation symmetry, or we consider a ground state where we have translation symmetry, rotation symmetry, and whatnot. And then we can also look at constraints coming from those type of symmetries, relations between operators, and yeah, that will be also an interesting way of taking this method further. But yeah, let me stop here and thank you for your attention.
Okay, thank you, Jorrit, for the very interesting talk. We have time for a few questions.
Okay, I have a question, Jorrit. In the cases you consider the Hamiltonian loop not too complicated, in the sense that you had, like polynomial in X and P. So therefore, the operators you were choosing were like X to some power, P to some power, and so on. Have you looked at cases where the Hamiltonian is more complicated? And then I would imagine that it would be non-trivial to find what the interesting O's are, in the sense that, okay, for example, for the matrix model, it would be the O's which are related by the loop equations. and then you want to impose positivity on those, and they will not necessarily be something as simple.
Oh, that's right. Yeah, the matrices that I considered right here, or the Hamiltonians that I considered here, are rather simple. They still involve this trace p square, and there's not something funky going on, but the momentum. Yeah, what type of models do you have in mind?
There's things
exponential or something? Or,
yeah, for example, say that you put an exponential in your Hamiltonian, or
I see.
many exponentials and so on. Then like the loop equations or the commutation between H and O will not necessarily give you, like if you put O as X to some power, it will not give you, it will not relate X to some power to some other X to a different power.
Yeah, there will be an infinite sum, you're saying, because of this exponential and things like that.
Yes, or maybe there is a smart choice of operator that it will not be just X to some power, it might be something more complicated, but then it just relates these different operators.
Yeah, no, you're right. If that's right. If this Hamiltonian is going to be more complicated, then okay, this method might not be, or you might need to go to higher order and to get a convergent answer. I guess you could still wonder, like, okay, if I do this commutator and I get relations between different operators, then you could still run this program. If there's constraints that give you operators that do not, that sort of become bigger and bigger, and you need more and more constraints, then yeah, that might be more complicated to implement this. I mean, one of the sort of to justify this sort of simplicity of these models is that in the end, I guess the goal would be to apply this to BFSS, and that is actually pretty simple. Hamiltonian is pretty simple. There's just some fermionic coupling and fermionic, and there's a commutator square piece. So all these complications that I guess you're thinking about would not happen in this model, but they could definitely happen in other models that have more complicated exponentials. Yeah, I guess one thing you can do is maybe in the quantum mechanics case, just do this for some cosine hyperbolic type potential or whatever.
Yeah, for example.
Yeah, that would be interesting to see how that works. Yeah.
Okay, thanks.
Yeah, thanks, Bernardo. That's a good question.
I think Pavel has a question.
Hey, Pavel.
Hi, Jorrit. Thanks for this nice talk.
Thanks.
So actually, maybe it's related to the previous one. So I was wondering, like, what would happen to this program when you apply it to more like holographic setups, or maybe even in terms of quantum mechanics? Let's say if you take some kind of chaotic model or maximal chaotic model, in a sense that even, for example, quantum mechanics with some inverted harmonic oscillator that has something like out of time order correlators to be like growing very fast and things like that. Would you expect that this all should not apply, or like this is becoming too complicated, or maybe, this kind of?
Yeah, so of course the inverted harmonic oscillator is very important for the CS1 matrix model, and in that case, I think we looked at this. I think the conclusion was that it seemed to work, even in that case. But yeah, those results are preliminary, and okay, I'm not 100% sure what the exact status of that is. I mean, it's it's a bit surprising that it works because the potential is unbounded, and why would this ever converge to anything? But one thing that I think this is what we tried. We if you have the inverted harmonic oscillator, you can cut it off at some very low value. so very negative value, and then the program does still work. And then the question would be, okay, what happens when you take that cutoff away? I think that would be a way to regulate this problem that you're thinking about. So I would expect that for each cutoff that you pick, this method would work. But then the question becomes, okay, what happens when you take that cutoff away?
Nice.
Yeah.
And sorry, maybe I had one more question. So, so usually we think about some models at n infinity as being like either solvable or close to solvable. But somehow, like you're studying model with n infinity that is nowhere close to solvable, or maybe are you like asking questions that would be difficult to answer even in the even if we solve that model? Can you just clarify this confusion?
Yeah. So the of course the one matrix model is just solvable, but the one matrix quantum mechanics is exactly solvable because it maps onto this free fermion system. But that's because we can diagonalize this matrix, right? And if we look at more matrices, then we can't do that trick anymore. And we can only write down, like we can diagonalize one matrix and then like ask about the behavior of the other matrix in the effective theory when we integrate out these there's one other matrix. And so that doesn't really care about infinite n or whatever. So that sort of prohibits us of solving that model exactly. In the matrix model case, there you can still there is versions of matrix models that are solvable, even if there's multiple matrices. There's this particular formula for integrals of those types with two matrices. It's this Harishchandra, the Subert, and some other people. They derived the formula for two matrix, or I think it's any matrix matrix model that has a. But I'm not too familiar with that. But there's definitely in the matrix model case, solvability is much better. Here in the matrix quantum mechanics case, yeah, it's just this issue that you can only diagonalize one of them, and at infinite n, it's still non-trivial. And BFSS is in that same ballpark, and that is also still very complicated to solve, even at large n.
Okay, thanks a lot.
Yeah, no problem. Thanks for the question.
Okay, I think in the interest of time, we're going to stop the recording here. But before, I would like to thank you again, Jorrit, for the very nice talk.
Yeah, thank you.